Welcome to AP Daily Topic 3.1, Intermolecular Forces, Video 2. In this video, we will discuss hydrogen bonding and ion dipole interactions, two specific types of intermolecular forces of great significance. I'm Kristen Cacciatore from Charlestown High School in Boston. So today we're going to start off by looking at a series of 4 molecules, hydrogen compounds of group 16. So first of all, I want you to remember that all of these molecules have bent molecular structures, so they are all polar. Because these molecules are polar, they all experience LDFs and dipole-dipole forces. Now, look at the graph. If we go from H2S to H2SE to H2TE, the molecules get heavier and the boiling points increase. And this makes sense because as they get bigger and bigger molecules, we get more polarizable electron clouds and therefore stronger LDFs and higher boiling points. But there is an anomaly on this graph, and that's water. Water is the smallest molecule, but it has the highest boiling point. So why is that? Well, it's because water molecules experience a third type of intermolecular force, which is called a hydrogen bond, and those are stronger than dipole-dipole or LDFs in molecules of small size, and that gives it this really high boiling point relative to the other compounds in the group. All right, hydrogen bonding, what is it? Well, it's actually not a bond, so that's why you see the sarcastic quotes there in the title, because it's an interaction between molecules, not within a molecule. So it starts when the oxygen atom in a water pulls the electrons away from the hydrogen atoms that it's bonded to because of its high electronegativity. Now you remember that a hydrogen atom has only one electron to begin with, and when it's pulled away so strongly, it leaves essentially a bare proton there. And that strongly attracts the oxygen atom on a nearby water molecule, which is partially negative due to the polarity of water. And so that is what causes this hydrogen bond. And that is a strong type of intermolecular attraction represented by the dashed line here. All right, so I already said it's an unusually strong type of dipole-dipole interaction. It's not truly a bond. It only takes place between an H atom that is covalently bonded to a highly electronegative atom, meaning N, O, or F, and a highly electronegative atom on another molecule. So you need to have both, that H bonded to an N, O, or F, and then on another molecule, an N, O, or F to attract the hydrogen. It is possible to have hydrogen bonding within a molecule, but it has to be atoms that are far enough apart on the molecule for them to essentially reach around the molecule for it to conform in such a way that that's possible. All right, so now we've got this very complicated looking diagram. We've got 4 different molecules here and 5 labeled positions. We're going to try to decide if each of those labeled positions is hydrogen bonding or it isn't. So let's look at number 1. We've got a hydrogen atom that is covalently bonded to an oxygen atom. So that meets the first condition for hydrogen bonding. And then, so that is a covalent bond, right? It's pointing to that black line. So that's not a hydrogen bond. A hydrogen bond has to be between atoms on different molecules, or at least very far apart on the same molecule. All right, now number 2. Well, now we're looking at that same hydrogen atom, but this time the interaction is between the hydrogen and a nitrogen on a different molecule. So that is a hydrogen bond. How about number 3? Well, number 3, we've got a hydrogen atom and an interaction with an oxygen atom that's far away on the molecule. But notice that the hydrogen atom in number 3 is not bonded to an N, O, or F. So this cannot be hydrogen bonding. All right, how about number 4? Well, in number 4, again, I have a hydrogen atom and an interaction with an F atom, a highly electronegative atom on another molecule. But again, that hydrogen atom is not bonded to an N, O, or F. And so there can't be hydrogen bonding there. Lastly, we've got number 5. Here we have a hydrogen atom that is bonded to an oxygen atom covalently, and then it's interacting with an oxygen atom on a different molecule. That is hydrogen bonding. Both criteria are met. Hope these examples helped you. All right, now we're going to look at ion-dipole interaction. This is a different kind of intermolecular force. It's also very, very important in our world. So when ionic compounds dissolve in aqueous solutions, the dipole of the water interacts with the charged ions and causes them to separate. That's how solution happens for ionic compounds. The interactions between the ions and the water are called ion-dipole interactions. And they are even stronger than hydrogen bonds. These are very strong interactions for IMS, for sure. All right, so let's look at this diagram closely. On the left, we've got a chloride anion. It's negatively charged. And notice that the water molecules surrounding it are oriented so that the partially positive hydrogen atoms are pointing toward the negative chloride ion. On the right side, we have a sodium cation, which is positive, and there the water molecules have oriented themselves so that that partially negative oxygen is facing in. Again, these are Coulombic attractions, so opposites attract. All right, so let's look at an example. We've got Lewis diagrams and boiling points of ethanol and dimethyl ether. These are isomers, so they're both C2H6O, but notice that their structures are different. And notice that they have very different boiling points. Our question says, explain the difference in the boiling points of the two substances using principles of molecular structure and intermolecular forces. All right, I want you to stop the video and try this problem on your own before we go over it together. Okay, so how are we going to explain this large difference in boiling point? Well, notice that the ethanol molecule allows for hydrogen bonding. So two ethanol molecules in this substance can hydrogen bond with each other because you've got oxygen bonded to hydrogen. Whereas in dimethyl ether, the oxygen atom is in the center of the molecule and not bonded to any hydrogens. And so there's no hydrogen bonding possible. And that is why ethanol has a much higher boiling point. The hydrogen bonding leads to stronger IMFs overall, and therefore it's more difficult to vaporize the substance. So both molecules are polar. They're going to have similar LDFs because they have similar molar masses and therefore similar sized electron clouds. Ethanol can hydrogen bond because it's got that H bonded to O. Dimethyl ether cannot hydrogen bond. And the hydrogen bonding in ethanol means that the molecules experience stronger attractions and are harder to separate into the gaseous state. Thank you for watching.